Right now, Lake Michigan Huron is at a record high water level. And I've got some pictures here to show you Lion Head on the western shore of Georgian Bay, the lighthouse. This January, it was completely destroyed by the high water levels combined with a winter storm. No more lighthouse. If we go up to Perry Sound this April, there were high water levels and the wind was coming in from the west, and it pushed a lot of water into the big sound and flooded out the main town pier. Up in Point O'Barrel at the same time, again on the eastern coast of Georgian Bay, the water levels were right up and over the government docks there with the high water levels combined with the wind setup. So people all over Georgian Bay are seeing high water levels. But let's not forget that last year Lake Ontario also set a record, which resulted in a lot of coastal flooding. These are some pictures from the IJC's water level seminar a couple of weeks ago. But on the American side of Lake Ontario, over on the Canadian side of Lake Ontario, and also downstream, just above Montreal on the St. Lawrence River, lots of flooding occurring. There's lots of water in the system right now. Lake Erie set a record last year. Lake Superior tied its record high. There's just a lot of water in the watershed right now. But if we think back to 2013, Lake Michigan Huron was at record low water levels. And we had quite the opposite problem. Challenges getting to boats and docks and waterfront properties and so on. In some places, there was a lot more beach. Of course, that's not always good if you have a boat. This is Door County down in Wisconsin. And down in the Windsor Yacht Club. So a lot of variation is going on. And really today, we wanted to answer or give you some information towards answering the question of what is happening. There are two main points that I want you to take away from this seminar tonight. And the first of these is that researchers that are taking all of their time, spending their careers looking at the hydrology of these lake systems and climate science believe that these rapid transitions between these extreme water levels are starting to represent what is going to become the new normal. And also the second point is that past conditions around the Great Lakes are not really a reliable basis for decision making that'll carry us into the future. And the reason for that, of course, is that we have introduced a whole bunch more energy into the atmosphere now through climate changes. So the first slide here is talking about the water levels and the drivers of water levels. There are many things that combine and interact and synergistically or in opposition play around with each other to make changes to the water levels. We don't have time tonight to go into all of these, nor any really in a great amount of detail, but we do want to touch on some of the highlights, like the global warming and this increasing energy in the atmosphere, the impacts on precipitation, snow, rain, and cloud cover, how evaporation is being affected, and how evaporation also affects the water levels. We'll touch a little bit on the diversions to show you what's coming in and what's going out. The connecting channels, of course, lots of talk about the connecting channels between the lakes. I'll introduce you to those. The isostatic adjustment, the rebounding of the Earth's crust, we'll talk briefly about. And also then we'll talk about, from a regulatory perspective, the things that go into the considerations of managing these control structures that exist at some of the connecting channels. So I'll talk about these in high level, and hopefully by the end of the presentation today, you'll have a good solid basis. Heather already asked you or mentioned to you that we would be sending around a survey. If you're interested in diving into any of these in more detail, please indicate that on the seminar survey and send it back to us, because we'd love to talk to you in more detail about all of these types of parameters. Now, if we go back 10,000 years in the watershed, Lake Superior, Lake Michigan, Lake Huron, and Georgian Bay were all basically part of one big lake called Main Lake Algonquin. And they drained down through the St. Clair Basin, kind of out into an early proto-Lake Erie, The Niagara River connected the Lake Erie, the early Lake Erie to early Lake Ontario, and then those lakes kind of drained out through the Champlain Sea. But by 2,000 years after this, the glaciers had moved north far enough that we actually ended up changing the hydrology. So if you look here, the dark arrows indicate that the water flow from Lake Superior was actually going out through North Bay into the Ottawa River, and then down to Montreal and out into the Atlantic Ocean. No water was really flowing out of Lake Huron anymore into Lake Erie, but Lake Erie was still draining into Lake Ontario, and that was going out through the St. Lawrence River, or what would become the modern St. Lawrence River, and out into the Atlantic Ocean too. So kind of two different components here. So over time, there's been lots of change, and as that ice melted, the weight of that ice removed itself from the North American shield here, and you can think of the land as actually kind of tilting up. As that weight was released, this red line through the center of this chart shows kind of a neutral axis. The orange colors at the top are where the ground is actually rising. It's rebounding up. And if you look at the northern parts of Georgian Bay here, it's about 36 centimeters per century that it's rising. And then if we look down in the Chicago area, you can see that the relative sinking of the land down there is about 15 centimeters per century. So that means in Georgian Bay, as this land is rebounding, it makes it look like the water level should be dropping. And down in Chicago, it looks like the water level is rising. So we are going to see these big kind of time series changes. But of course, there's absolutely nothing that we can do about that. Humans can't intervene yet in that kind of a process and have any impact whatsoever. And that brings us to the basin that we see today. And this basin is all connected from the tip of Lake Superior all the way through the lakes, over Niagara Falls into Lake Ontario and down through the St. Lawrence River to the Atlantic Ocean. It's one big system. But if we look at it kind of on side at an elevation, you'll see that there really are kind of two distinct sections to this. And the important note here is that nothing that happens to Lake Ontario water levels is going to impact directly the upper Great Lakes water levels. There's a 100-meter drop at Niagara Falls, and even if water levels went up 10 meters in Lake Ontario, that would have no effect on the water levels up in the upper Great Lakes. Of course, the reason for Lake Ontario rising would probably be precipitation and things like that, which might impact us, but there's no direct impact from Lake Ontario water levels on the upper Great Lakes. But the upper Great Lakes, Lake Superior, Lake Michigan, Lake Huron, Lake Erie, they all do directly impact the Lake Ontario water levels because the water flows downhill and everything that's up there eventually is going to go over Niagara Falls, and that will have an impact on the downstream lower watersheds. When we talk scientifically about water levels, what we really talk about are the water budgets. So water budget is how much water is coming into a lake system and how much water is going out. And for our discussion tonight, we're going to focus just on the kind of Lake Michigan, Huron, and Georgian Bay. We call that one big lake. It's Lake Michigan and Lake Huron. We call it Lake Michigan Huron because that 6-kilometer stretch at the Straits of Mackinac really connect both lakes. And so the water levels in Parry Sound or Midland are the same as the water levels in Chicago, with minor variations because of wind direction and things like that. So when we talk about the water budget, we actually talk about runoff coming in. We talk about rain that's falling over the surface of the lake and landing right on the water. And then we talk about evaporation and things that are coming off of that lake surface. The second part is also to talk about the connecting channels. So the water that actually flows into a lake from the lake upstream of it. Of course, the Lake Michigan Huron have water flowing through the St. Mary's River from Lake Superior. And you can see as these green bars go downstream through the system, they get bigger and bigger and bigger. And that's because they include the upstream lake inflows, but they also include all of the rainfall that falls in the basin around those systems. So we would expect to see that, and of course we do when we look at the scientific record. Now, precipitation can fall, as I mentioned, right on the ground. And if it does, some of it might percolate through the soil into the groundwater table. That may run into rivers or help feed rivers. We also get water that directly runs off the land and goes into the rivers and streams. Sometimes precipitation is going to fall right on the lake surface. And that overlake precipitation plays a big role, especially in Lake Michigan-Huron, because by surface area, it's the largest Great Lake. It's 117,000 square kilometers. So there's a lot of surface area for that water to fall on. And then water either flows out through one of the downstream connecting channels, or it can evaporate off the lake surface, or actually be transpired off of the land. And this is part of the process where trees and plants take up that water through their root systems up into the leaves. And when they metabolize, they can actually release that water directly into the atmosphere. So depending on the type of ground cover that we have, there may be more or less evapotranspiration, as it's called. And that does have impacts, and you'll see some numbers relating to evaporative losses in a little bit. Another thing that we can't leave out nowadays is, of course, the conversation of what's happening from a global warming perspective. And while these numbers would not actually have been produced by a satellite back in the 1800s, here in current day temperatures, you can see that these are based on satellite readings that we can take, and it's a dramatically different planet. From the 1800s to the 2000s, we see a remarkable increase in the temperature, and of course that relates directly to how much energy is being trapped up in the atmosphere. So if we look at that from a graph perspective, and we take the average of all of the last century from 1901 through 2000, and we plot all of those values against that average of the century, you can see in the late 1800s and early half of the 1900s, predominantly temperatures were lower. And as we get to the latter part of the 1900s and into the 2000s, you can see the temperatures are higher. In fact, 18 of the 19 hottest years on record have occurred since the year 2001. And of those, the last 5 years have been the hottest ever on record. We could have said that same thing last year. The 5 previous years were the hottest on record. And it looks like we're going to be able to say that this year, because so far we're on track for 2020 to be either the first or second hottest year on record. Already we had records in March and April. So it's something that we have to really consider. That's a lot of extra energy. And if we look at that from the perspective of where these temperatures are, even though April in the Great Lakes area seemed to be a little cooler than normal with that blue over Canada and the Great Lakes area, globally, when we add it all up, you can see we had counteraction for more heat over in North Asia and Russia, lots of extra energy there. And so the average was actually 1 degree hotter. And again, the second hottest record, April record. So globally, floods and extreme rainfall events are now occurring about 4 times more often than they did in 1980. When we look at record-breaking precipitation, these are kind of the anomaly, huge precipitation events that happen. We can see that those record-breaking events are increasing in occurrence. And lest we think humans don't have anything to do with this atmospheric interference, this COVID shutdown actually created some opportunities for us to look at how humans impact pollution levels and different types of gases that get into the atmosphere. And we can definitely see remarkable differences either in northern Italy, in this case on the eastern seaboard of the US, looking over New York, or in China. We can see remarkable differences kind of before COVID with the activity that was going on, and then during COVID as these shutdowns started to reduce that amount of activity. So humans definitely have something to do with this. If we distill all of that kind of global information and bring it down to the Great Lakes Basin, what we can actually see is that the temperatures have increased on average about 2.3 degrees since the 1950s. We have about 16 extra days, frost-free days. The total amount of precipitation is increasing by about 14%. And these increased heavy precipitation events are up by about 35%. And I'll show you some figures and some graphs and charts that give you a good visual representation of these. The other thing to keep our eye on is that when we forecast out the emissions impact, so the emissions of carbon dioxide and other kind of global warming and heat trapping gases, what we're seeing is that there are potential changes in the number of days that exceed 90 degrees around the Great Lakes. This would be only about 0 to 10. in that light yellow, but around Georgian Bay especially. But if you look down around the southern Illinois, where it's really a dark red, what we're talking about there is 70 to 80 days per year that would be in excess of 90 degrees. That's the increase. So all of the storms that track up from the Gulf of Mexico really pass right through that area and come right up over the Great Lakes. And so we would expect those storms to have more energy. And of course, if you talk to tornado spotters and people that watch those kinds of storms, they do expect to see a lot more activity like that up in the Great Lakes region going forward. We are already measuring increases in the actual water temperature in Lake Michigan. Specifically, here is the graph of Lake Michigan. You can see that about over a degree of temperature change since 1995. So that's a very significant thing if you're a fish or some type of aquatic organism. And in some case, that's an enormous amount of stress to put on those types of organisms. And if that goes much higher, it can even end up being fatal for certain organisms. I said I would show you the precipitation in a little more graphic way. So the next three slides are really the US precipitation here. I just want to draw your attention up to the little strip between Lake Superior and Lake Michigan. This dark green color represents the record wettest period of time. So 2017 from January through December, that was an all-time, that was the wettest year ever in that area. Anywhere where you see dark green, that's what it means. Anywhere where you see the lighter green, it's almost up at that level. It's much higher than average. And then again, as you go to the orange colors, that's on the opposite end, kind of a drier type of condition. But in the Great Lakes area, you can see there's a lot of heavy rainfall. I'm going to advance this to 2018. And again, you'll see on the eastern coast of Lake Michigan, there's a cell of increased precipitation there. Most of that rain that year was falling down in the eastern seaboard of the United States. And right in that space, the actual watershed of Lake Michigan Huron is fairly narrow there, but there's still, record rainfall. And then again, advancing it to 2019, we can see if you look again at that little strip between Lake Superior and Lake Huron, another record. In other words, there was a record set in 2017, and that record was again broken in 2019. So there's been lots of water falling into the watershed. And in fact, if we look at this chart, we can see in each of the dots on this graph represent the previous 3 years combined precipitation. So to smooth out the year-to-year variations, we add up the previous 3 years and then we plot it. And then the next year we move forward, drop the oldest year, add the new year, and plot it. And what you can see here is that the last 3 years, and I'm creating this little gauge so that you can get a sense of the height, the change, over that 3-year period, there was a lot of rainfall that fell in the basin. The other thing to draw your attention to is the dark solid line that's rising from left to right through this figure. That's the trend line, if you will. And the trend in precipitation has been increasing since 1903. So we're seeing more precipitation, and then on top of that increase in average, we're also seeing this huge amount of rain comes in. And if we take that figure and actually transpose it into all of the other periods where there was a 3-year rise, you'll see that we never ever exceeded the amount of rainfall that we've received over the last 3 years. We received more rain in the last 3 years than at any time previously in the recorded data for the Great Lakes. So that's a significant thing, and really that's the main part of our story today. Is there's just a lot of rainfall that's been happening that's entered the basin, and it has to go somewhere. It's going into the lakes, and then each lake sends it downstream, and by the time it gets to Lake Ontario, it's accumulated a lot of extra water. We're also seeing changes, though, if we look at the water equivalent. So this would be if you took the snow that's in the forest and you melted it, how many inches of water would you have, or how many centimeters of water would you have? And you can see that there are changes, especially in Lake Superior, as to when that snowpack is melting. And it's getting earlier in the year, and in some cases there's hardly any snowpack left. In the case of the most recent times here with the blue line, you can see that it's well below kind of the prior years, the historic period. So that's anecdotally what people are reporting too, right? Is that there's just not much snow in the woods. And so the spring freshet, or that spring runoff, is diminishing, especially in the months of April. We're seeing kind of a trend towards drier Aprils. Now we can measure groundwater. There are interesting ways of doing that. This particular methodology uses a gravimetric satellite, a couple of satellites up in space, and as they float over the planet, they actually can measure these slight changes or perturbations in the Earth's gravitational field. And that can be used to give us some assessment of how much groundwater there is in the watershed. And of course, in the Great Lakes Basin, you can see a lot of blue. That means a lot of water. So the groundwater is already, getting towards that saturation point, which means when these big storms come through, there is no ability for the ground to soak that water up, and it's just immediately running off into the bay or running off at a higher rate. So lots of water in the watershed. Now, one of the other things we need to talk about are diversions. In this case, there are two that are up in the north part of Ontario, above Lake Superior. One is called Ogoki, the other is called Long Lac. These were diversions of water that used to flow up north into James Bay, but back in the 30s and 40s, 1930s and 1940s, they were changed in their direction, and I'll bring you back in a second to some pictures there, because we also have to talk about other diversions. There are diversions that people discuss in the public or you see in the press. For example, Waukesha, a little community that's right on the boundary of the Great Lakes, Lake Michigan watershed and the Mississippi River Basin watershed. And a diversion like that is actually, there is water taken out of Lake Michigan, but that water is actually recirculated and put back into Lake Michigan. So it's a diversion, but it's not water that's supposed to leave the basin. There's a Great Lakes Compact, which is made up of the 8 Great Lakes states and Ontario and Quebec. And there is a resolution there that there should be no water that gets diverted out of the Great Lakes Basin, but there are some exceptions. And of course, it's the exceptions that make people nervous. So that's a whole different discussion that people can have about should those diversions be allowed or not. But if they're well regulated and if they follow their rules that they're supposed to when they're granted these diversions, that water really does come back into the system. The Ogoki and Long Lac diversions, again, I mentioned originally, these are rivers that used to flow north to James Bay. In the case of Ogoki, this river system was diverted into Lake Nipigon and then out into Lake Superior. Back in the 30s and 40s, you remember there was the Second World War going on, and predominantly this was designed to send more water into Lake Superior that could be used for power generation, even as far away as Niagara Falls and Montreal. And the Long Lac diversion similarly took water that would normally have gone north and put it into Terrace Bay in the north shore of Lake Superior. That was predominantly, in part, it produced some power for a pulp mill, but it was also to float the logs downriver to get the logs to the pulp mill. And of course, nowadays, they're trucked. So those are two diversions bringing water in. This is a picture back in 1943 of one of the finished structures up in that area. And we'll talk about the connecting channels and Chicago in a few minutes. Declining ice cover is happening in the Great Lakes. In fact, some published data from NOAA a couple of years ago showed that the number was about a decline of 71% since the 1970s. You can see a general trend line here towards less ice, but with a lot of variability. There are some years where we have lots of ice and other years where we don't. And this year, at 2020, in February, we reached the maximum for the winter. It was only 19.5%. So again, 2020 was a low ice year, and that continues towards this trending. Although in 2019, we had up to 80% of the lakes covered in ice. Now, it's not just ice that's important. It's what kind of ice is on the surface. Because if you have the black ice that you see in this figure in the bottom right, that's a solid sheet of ice. It does give a separation between the wind, winter winds that are blowing across the lake surface and the water that's trapped underneath the ice. But if we get up into brash ice or some of these other kind of patchier ice conditions, there's still the ability for some evaporation to occur in those times because the wind can kind of get turbulent in around those things. There's more open water, etc. So being able to not only understand whether there's ice or not and what percentage of cover there is, the people that are doing these models and calculations for what's going to happen to water levels really have to understand what type of ice is there. And they rely on instrumentation against satellite systems as well as ground truthing observations. But these satellites can actually use radar and scan the surface of the water and actually see what kind of ice coverage is there. What's the type of ice that's on the water? And that's important for putting it into their equations. Faster wind speeds have a big impact on evaporation especially, but we are seeing wind speeds that have increased on average 5% per decade since the 1980s. And it was only, I guess, 3 years ago now, in my marina in Midland, we experienced for 15 minutes a hurricane force 1 wind. These are the kinds of energies that are starting to hit up in the Great Lakes region. When we have faster winds, of course, this can create more wave action. If this wave action occurs in the wintertime, when there's no ice on the lake, it can actually disrupt the fish eggs that have been laid and cause a lot of kill-offs of fish eggs, like whitefish and lake trout and so on. But we see winds can increase the wave action. And if you're on one side of the lake, as the photo I showed you earlier up in Perry Sound, if that wind is blowing from the west, it can pile the water up on one side of the lake, so the water level looks like it's rising. But on the other side of the lake, the water level actually drops. And these are waves that actually get set up in these basins that we call seiches, and they can slosh back and forth even after the wind drops. Sometimes people can remember even standing there and watching the water kind of go down about 6 inches over an hour and wonder what's going on. And it can just be the wave action that gets set up there. And that wave action on the bottom image here on the right, it doesn't always just occur in the top water. In the summertime, we know if we dive down deep in the water, there's kind of a band called the thermocline, below which the water is really still cold and above which is kind of the warm surface water. That acts as a separator between those two water bodies, and you can end up with a wave in the bottom cold water sloshing back and forth. And again, even though the surface water looks still, sometimes you can see water levels change just because of the fact that there is this sesh in the bottom waters. So that can be a little way that water does change, and you see that. Now, of course, the Great Lakes also do have a tide, but the tide is only a couple of inches. It's measurable. You know, scientists can actually spend their time and try to tease it out, but it's always masked by other environmental variables, wind and setup and wave action and that kind of thing, right? So while the Great Lakes technically have a tide, it's not something that really contributes much to the actual water levels, but it is there. Now, I mentioned that faster winds can increase evaporation. Here's a picture, a satellite image from February a couple of years ago. And you can see as the water is evaporating out of Georgian Bay and Lake Huron, it's actually getting swept right out of the basin, down over Lake Erie and out over the eastern seaboard of the United States. And in fact, I do have one image that's not in the slide deck, but it showed it going right out over the Atlantic Ocean. So that's water that is in Georgian Bay that's going directly into the Atlantic Ocean. It's not flowing through Lake Erie and into Lake Ontario and down the St. Lawrence River and through Montreal and past Quebec City, right? It's coming right out of the watershed immediately. So those evaporative losses can also have some impacts that make it really tough for the scientists and modelers to figure out what the water levels are going to be. We used to think of ice really in a very simplistic way. We used to think of it as kind of the lid on a pot. So in years where there wasn't much ice coverage, we used to think that a lot of water was evaporating out of the system. And then in years where there was a large amount of ice, it was like putting the lid on the pot, and that was trapping all of the water from evaporating. That's not actually how we view ice and ice coverage anymore. It's a little simplistic. We really are looking more from a thermodynamics perspective now at ice and its impact on the heat in the water, how heat is used to change water from a solid ice to a liquid water, and then from a liquid water into a vapor. And that thermodynamic process really is driven by the energy that you put into the system, the temperature difference between the water and the air, and by the relative humidity, how much water vapor is already in the air, and how easy it is it for more water to evaporate. So if we have years with a low amount of ice cover, it means the water is probably going to stay a little bit warmer. That's going to have some evaporative impacts. And then the next year, that warmer water carries in, and there's more heat loss because the water is a lot warmer than the colder air coming into the winter air that comes down. That winter air then can pick up a lot more water out of the lake. That can elongate the ice coverage period, which then leads in the spring, as all of that extra ice starts to melt, cooler water temperatures and lower amounts of evaporation. You can see it's pretty complicated how all of these patterns play one into the other, and each year is dependent on the previous year. So the new model is a little more complicated, but it takes into account these energies. And just to use the standard, 1 calorie of heat could take 1 gram of water and increase it in temperature by 1 degree Celsius. That's 1 calorie. That's just the definition that we use. But to change ice, solid ice, into liquid water, it actually takes 80 calories. So 80 times the amount of energy. So if there's lots of ice, it takes 80 times the energy just to take that ice from solid ice into liquid water without even changing the temperature, just changing state. And then of course that water would have to be heated up again, and that's when the heat would start. When that water at 20 degrees is evaporated, so when the sun is hitting the water in the summer and we see some storms starting to form, we actually are taking 585 calories to evaporate 1 gram of water. That goes up into the sky, and when it turns back into a water droplet, it releases that energy. So the lakes are acting like these heat pumps, moving enormous amounts of energy from the lake water up into the atmosphere and back again. And if we think about the impacts of increasing global temperatures, so if a 1 degree Celsius temperature increase happens over the Great Lakes, that mass of air can actually hold about 7% more water vapor. And in other words, it can take up more energy and hold more energy up in the clouds above. And these storms that's the reason why these storms are getting bigger and more energetic. One of the other things that really is critical when it comes to evaporation is when does the evaporation occur? So here's a plot of a number of years and what the evaporation looked like from the Great Lakes, specifically in this case, Lake Superior. You can see the first year of 2008, 2009 is this thin solid line, and its evaporation was during a high ice cover winter. So there was lots of ice that winter. The following year is this darker solid line right beside it. That was 2009, 2010, and that was actually a low ice winter. So there's a high ice winter and a low ice winter, and yet we can see the evaporation was fairly similar. But when we look at 2010 and 2011, we can see a remarkably different type of evaporation happening. And what really happened there, if you look down at this bottom section of the gray, the early evaporation season, it started to evaporate earlier. It was a warm summer. And as the fall air came in and got cooler over that warm water, the evaporation started happening earlier. And that made an enormous amount of difference. If we actually delayed that evaporative start and just kind of moved that line over to the other years, you can see the evaporation would have been pretty much identical. But because it started earlier, there was a lot more, an extra 10 inches of evaporative loss over Lake Superior that year. So when the evaporation happens can also be very important. Again, that's all thermodynamics. The connecting channels, the ones for our discussion today are really at the St. Mary's River. Here's the looking from Lake Superior eastbound down the St. Mary's River, Canada on the north, US on the south. We have the St. Clair River, which is at the bottom end of Lake Huron. And here we are looking north towards Lake Huron from the St. Clair River. I'll just zero in on the Blue Water Bridge. You can see here that there are, on both the US side and Canadian side, kind of hard structures. The shoreline is not a natural riverbed. It's just kind of a connecting channel, more like a canal. But there are no control structures whatsoever here, unlike up at the St. Mary's River. And then if we go to the Niagara River, Any water that ends up coming from Lake Erie and flowing into the Niagara River is destined to go over the falls or through the power dams and be used as power. But there are no control structures here that actually impact water levels. Technically, they might be able to do 1 or 2 inches, but that's the limit. There's no water control structures really here other than allocating water into the power dams or letting it go over Niagara Falls for the tourists to see. The other downstream connecting channels in Lake Ontario and the St. Lawrence River, we won't worry about today in our conversation. We're just kind of focusing on the upper watershed here. But water that enters the Niagara River, as I said, it's going to go over the falls or it's going to go through the power plants. Now, we take all of those parameters, all of those issues, all of those features, all of those measurements, and we actually now have to try to combine them into a number. And when we talk about that number, we talk about the net basin supply. So what's the sum total of all the water coming in? What's the sum total of all the water going out? And whatever's left over is going to have the impact on water levels. If it's a plus, if there's extra water staying in the system, the water level is going to go up. If there's more water leaving, obviously the water levels are going to go down. And if we look at these numbers, they come from the US Army Corps a couple of years ago. So these are kind of just average representative numbers of Lake Michigan Huron. You can see we have in blue the Lake Superior outflow that comes through the St. Mary's River into Lake Michigan Huron at about 75,000 cubic feet per second. We have runoff that comes off the land, about 94,000 cubic feet per second. And then we have the rainfall that lands right on that 117,000 square kilometer surface, so 110,000 cubic feet per second. And leaving Lake Michigan Huron through the connecting channel at the St. Clair River, we have about 189,000 cubic feet per second flowing out. Now, the yellow line above that, 87,000 cubic feet per second, almost half as much as is flowing out of the St. Clair River. That's evaporating off that huge surface area. So there is an enormous amount of impact that evaporation can have. And it's the balance between precipitation and evaporation and all of these other parameters that actually dictates what happens with water levels. If we add the diversions in here, just so we can see the Ogoki and Long Lock diversions bring in about 6,000 cubic feet per second, depending on how they're being operated. And the diversion at Chicago, which I mentioned we talk about in an earlier slide, is taking out only about 3,000 cubic feet per second. That's what they're allowed to take out there. So you can see we're actually diverting about twice as much water into the system as is leaving us through Chicago. And Chicago, of course, when water levels were really low, was a big culprit for lots of folks in the public, thinking that they were stealing our water. But we were still bringing Ogoki and Long Lock diversion water in there. So we're actually bringing more water into the system than we take out from a human-induced perspective here. When we take all of those calculations, the net basin supplies, and add all the pluses in and take all the minuses out, and produce a plot for each month, you can see here at the top, we've got Lake Superior. The second set of bar graphs is Lake Michigan Huron. Then we have Lake St. Clair and Lake Erie and Lake Ontario. You can see where there's blue bars, it means that there was a positive net basin supply. There was more water coming in and staying in the system than leaving. And wherever you see red bars, that means that there was more water leaving the system. The net basin supply was negative. More water was evaporating or flowing out. And you'll notice in the Lake Michigan Huron graph in particular, its scale is a lot bigger than the Lake Superior scale or the Lake St. Clair scale or any of the other lakes. So these bars are bigger, but relatively they're even larger. It's just that we're using a different scale on this particular graph. And predominantly you can see in the 2018, 2019 kind of time frames that there's more water that's been staying in the system. The net basin supply has been quite large, and that's why we have high water levels now and are setting records. When we talk about water levels, we really have to talk about a couple of things. Water levels fluctuate, right? Wave action goes up and down, and we see water levels changing, but that's kind of the average water level. And we see that represented in a minute in the scientific plots that I'll show you as a green arrow. The water levels fluctuate between kind of the typical high water levels and the historic low water levels. Those fluctuations are within the normal boundaries of the lake. And in the case of Lake Michigan-Huron, that range can actually exceed 6 feet, a little over 6 feet of range, 2 meters. We also have periods of extreme, or the historic records, if you will, the all-time ever record high or record low. And then we have what are known as exceedances, or water levels that actually go well above those historic water levels into extreme lows or extreme highs. And so just these arrows are going to now be transcribed into this more scientific representation of the water levels. So here's our actual water level. This is a plot over 2018, 2019, and 2020, kind of 3 years. You can see the actual water levels are this red line. The long-term averages fluctuate, higher in the summer, lower in the winter. You can see that kind of fluctuation represented here. The actual variation between the low levels and the high levels, or the natural variability, if you will. The record setting periods, and this year we've set records in January and February and March and April, and we're going to set a record in May in all likelihood. I think I'm pretty safe in predicting that now. And even it looks like June and July and even into August. And then we have these exceedances, and these are the things that really start to make people a little nervous, whether it's on the high side or the low side. It's the unexpected water levels that go outside of these historic boundaries. And some of those are starting to be impacted by climate change and these increasing storm fronts that are coming through, the new conditions. So if we look at a description of the current conditions for water levels, the Great Lakes are pretty much at or near record highs. Lake Michigan-Huron was quite high, 7.6 centimeters above the previous record that was set back in 1986. So we'll be breaking that record. Lake Michigan-Huron in April rose about 7.6 centimeters. It usually rises by about 10 centimeters, but of course there's a lot of flooding going on nowadays too. So rise might not necessarily be the best representation of change in water levels, given that the surface area starts to increase, but we have to see the science on that. Lake Michigan-Huron's mid-May level was 86 centimeters above average, 18 centimeters higher than at this time last year, and it was the highest on record. And also 7 centimeters higher than that 1986 record. So that's like not just setting a new world record, that's like blowing that new world record away the next year. And then Lake Michigan-Huron is forecasted to likely exceed these historic means right through potentially even into August. So we are going to have to keep our eyes out on the high water levels. And again, just circling back on this kind of one of these 2 points that I really wanted to make sure I leave you with today. And that is that researchers who specialize in these areas and look at climate science and look at water levels and evaporation and all of these factors really are starting to believe that these transitions, these more rapid transitions between these extremes are going to represent new normal. And that may mean from year to year, water levels rise and fall faster. It may mean successive years keep getting rising more and more and more, or falling more and more, but there's a change here. It's not the old normal, it's the new normal. Finally, today I want to just kind of leave you with some thoughts around the compensating structures that are in the lake. This is a picture, a zoom in, of the compensating works at the St. Mary's River. They were built back in the early 1900s, and they were designed to actually allow water to be flowed into some power generating structures to make electricity. At the very bottom of this control structure, this first gate, you can see a solid wall going across the photo towards the left side there. That's on the bottom side of this photo, the inside of that particular wall. All of that water is kind of designated for fish habitat. So that particular gate, gate number 1, is to be maintained. There has to be a flow rate going through there for fish that use the St. Mary's River as their habitat. And then the other control structures, some of them are on the Canadian side and some of them are on the US side of the river, but they're maintained to allow water levels to be maintained on the St. Mary's River, as well as up in Lake Superior and also down in Lake Michigan. So when the organizations that oversee these, and these are control boards that are set up, the International Joint Commission oversees these control boards. they are mandated to take into consideration a number of factors when they look at which gates and how much they should open. The upstream and downstream impacts have to be considered before they're allowed to make any changes. Impacts on agriculture and commercial fisheries and commercial navigation, what would happen to the freighters that are coming up through the system or the recreational boaters, what the environmental impacts might be, i.e. The fish habitat that I mentioned a minute ago, any impacts that it might have on power generation and cooling water that's available for different facilities, industrial and commercial users, if there's consumptive or non-consumptive factors that might be at play here, municipal infrastructure, drinking water, sewage systems, First Nation rights, impacts on recreation and tourism and residential shoreline property, both on the connecting channels or the riparian landowners, but also around the lakes themselves in the littoral spaces. And then also they have to consider what the impact of ice damming might be. So if they just open the gates up and lots of ice flows downstream and starts to produce a dam in the river downstream that's uncontrolled, that could cause flooding and property damage and also damage to infrastructure. There's a lot of regulatory considerations that have to be taken into account whenever these structures are operated. And so they are driven by what comes together in a plan, a regulatory plan. So for specifically the St. Mary's controls, there is Plan 2012, and it starts trying to return water flows to what would have been there prior to the 1901 beginning of the construction. What did the natural state of flow look like there? So they need to, they think about that. They also have to apply a balancing principle. And it's a little misinformation out in the public, I think, that they never think about downstream users. They always think about downstream users. They're mandated to think about downstream users. So they must think about what's going to happen to people up in Lake Superior and stakeholders up there, and also what's going to happen to the stakeholders downstream in Lake Michigan, Huron, and respect the flow rates that might have impacts on both of those constituencies, if you will. They also have to follow and respect the actual physical operational limits of the system. The structures themselves are only capable of being operated at certain rates as maximums and minimums. And I mentioned, if you look at the bottom of that third point, every June 5th, there has to be at least 1,700 cubic meters per second flowing for the lake sturgeon to come in and actually use that habitat. So that's a consideration that has to be there. And then, of course, in number 4, all of the other uses, industrial and municipal users and navigation and the fisheries and hydropower and so on. So trying to take all of those different things into consideration, especially when here at the control structures, they're pretty much all represented. This is the border between Canada and the United States. There are the upstream users and the downstream users in Lake Michigan, Huron. There are 3 power generating facilities right at these at the mouth here. Shipping on the US side, the big locks. There's the ecosystem users. There's on the Canadian side a smaller set of locks, just slightly smaller craft, and the boating channel really. All of these constituencies are pretty much right in that area, and they all have to be taken into consideration whenever the International Lake Superior Control Board makes any recommendation on changing the flow rates. So balancing the water levels that are already high up in Lake Superior with water levels that are already high down in Lake Michigan, Huron becomes a very difficult task, very challenging, let's say. Down at the Niagara Control Board, again, the only thing really that they deploy each year from a in the water perspective is an ice dam to capture water to prevent it from going in and damaging any of the infrastructure for the power generation. But they can't, as I mentioned, control water levels with this. So they regulate when those go into the water and when they come out of the water. If you note in this picture of the Canadian Horseshoe Falls, you'll see a structure over here on the right side of the picture. That structure actually is just to maintain a pond of water for the intake into the Sir Adam Beck pipeline. So there's a big pipe or a big tunnel that was dug, and that structure that's in the river can't keep water from flowing either into the Adam Beck Dam or over Niagara Falls. It doesn't impact water levels in Lake Erie. It's just really to maintain a certain amount of water in that pond so that when needed, it can be flowed into the Surratt and back, either the reservoir or right into the power facility. So I hope that gives you kind of a big overview of some of the complexities that impact water levels and some of the drivers and the issues that are at play. We've covered a segment of these topics today. It would take a lot longer to go into great detail on many of them. But if you do have some interest in that, please indicate it in the survey, because we'd love to go into more detail and talk to you more about any of the facets that we kind of began to introduce today through this presentation. And again, just to reiterate and come back to these two main points, people that are specializing in this area believe that these rapid transitions are something that we're going to continue to see going forward, this new normal, if you will. And also the bigger point is that because of the huge increase in the amount of energy that we've got in the atmosphere, that's only really been happening over the last 100 years, but we're seeing the accumulation of that, especially since the 1980s. Looking back in time and seeing what my great-grandfather used to think of water levels and how water levels used to behave really is no longer a reliable basis for decision-making going into the future. So thank you very much. We're going to I'll mention briefly, Georgian Bay Forever. It's our 25th anniversary this year. We've been around since 1995, protecting the water and doing scientific research and public education like these sessions. We will take some questions if we have any now, and any questions that we are unable to get to tonight because of our time constraints, we'll happily put some answers together, and we do expect to publish this presentation so that you'll have it available going forward. So let's look just at a couple of questions. If you are interested, there's a chat area that you can type your question in at the bottom of the chat space. Okay, so we have a couple of questions starting here. There was a 1993 IJC levels reference study on crisis conditions that had recommendations for low and high water and recommendations on what to do in that case. That study actually didn't include climate change impacts. I don't think the IJC right now would be, they will have to speak about how they're going to interpret that study or what they would use of it. But from my perspective, without having the climate impacts taken into account, there'd be no point in implementing a recommendation from a study that was 30 years old. I think when I did ask a question like this to the IJC commissioner, the answer from the commissioner was that the regulatory authority that they've given to each of the control boards is being reviewed right now with climate change impacts in mind. And so we will be turning to the IJC to get a lot more information about that and those processes and see how we may be helpful in those cases. Certainly with disseminating that information when it becomes available. A question here about, based on our research, what are the projections for water levels for the next 3 to 5 years? Projecting water levels over a 3 to 5 year period is kind of like projecting what the weather is going to be like tomorrow. It's a difficult thing to do, and climate scientists don't use short-term periods like that, 3 to 5 years. We actually try to look at trends over decades, like a 30-decade or 40-decade, so 30 or 40-year period. And in those 30 and 40-year periods, we can start to see what trending is going to look like, but it's very difficult to forecast what a specific water level is going to be next year. Now, having said that, the models that are available through the National Oceanic and Atmospheric Administration or Environment Canada, the US Army Corps and so on, this unified group, they are pretty accurate looking out 6 months. So based on conditions around the globe today, the models can be fairly accurate in their forecasting of what water levels are going to look like over the next 6 months. But beyond that, this uncertainty starts to expand, and it's very difficult to make a precise projection. There are some models that are looking at water levels and what the new models that are coming out are not published yet. We are eagerly anticipating those later this year. There should be some new modeling out, but if we go back to the models that were used in the 2012 Upper Great Lakes study by the International Joint Commission, they did show that there was kind of a preponderance towards a long-term decline in water levels, but these increasing periods of flashiness. And we are already seeing that increasing flashiness that was predicted or modeled. And so the expectation may be over the long haul that water levels may decline, but we really are going to see some new data with current new computing systems and new information that will be coming out. I know one of the scientists at Environment Canada is working on it, and it'll be very interesting to see what those show. Another question here is, if there are compensating structures in place, can they respond fast enough to manage extreme highs or lows? So in that case, the answer would be no. If we just had a huge storm that we didn't even expect come into place, and we thought we could open the dam and let enough water out that it would equalize water levels everywhere, the time that it takes for water to flow from one part of the system to the other is measured in years. And so if we have good forecasting and good modeling, it may be possible that those structures, like are already used in Lake Superior and Lake Ontario, could be managed to help maybe carve off some of these extremes. But Lake Ontario already had these structures in place and still experienced flooding over the last 3 years because of just the amount of water that came into the system. So it does pose some very significant challenges, to say the least. I'm not saying it's not possible. We actually published a study that said it might be possible to help clip off the exceedances, the extreme highs and the extreme lows, but that would be it would require a lot more study in order to give a definitive answer on that. And maybe one more question, and then we'll call it for the evening. Yeah, so here's a good question. Given that water levels will be at record highs, will it be exacerbated by the expected increase in violent weather events? And the answer to that is yes. The answer to that is something that is being discussed at each municipality on the coastline of Georgian Bay, certainly, and all around the Great Lakes. When you have a lot more water, the infrastructure is susceptible to being overtopped. But similarly, back in 2012 and 2013, when water levels were at extreme lows, there was a pier in Burns Harbor, Indiana, the bottom end of Lake Michigan, $1 million pier that was eroded, like undercut. So these extremes, we haven't designed our coastal infrastructure anticipating these extreme highs and extreme lows. We were kind of used to what happened naturally. But now that we're seeing these changes, there's going to have to be a lot of resilience engineering, coastal resilience engineering undertaken. And there are some studies looking specifically at that coastal resilience and the impacts of these water level changes on the infrastructure there. So I think that's it for this evening.